I was not really surprised to end up in the machine learning session with this title, but nevertheless I took the opportunity to remind myself what machine learning is actually all about, and I asked Wikipedia, and Wikipedia told me it's the machine that learns something. And well, let's not kid ourselves. So in this session, it's not the machine that learns something. It's actually we as statisticians learning something from the machine. So what we are actually doing is we fit probabilistic models to data using very sophisticated optimization techniques, heavily influenced by computer science thinkings. But the core is always a probabilistic and thus a statistical model. So some people prefer the term statistical learning instead of machine learning, and as the famous epidemiologist Sander Greenland once pointed out, it has the same problem as the journal title Statistical Science. It's an oxymoron, so it can't exist. It's either statistics or it's science. And in machine learning, we have the problem that we either learn something really or we just estimate something. And it's the latter what we are doing. So I prefer the term statistical model because it's honest and it makes it explicit that we are fitting an underlying probabilistic model and we rely on the corresponding theory. And the problem is when you want to attract decent funding money, this is just too dull a term to be used. So then maybe we should stick with machine learning after all. Now, the goal is always to understand the statistical model behind a special machine learner, or learning machine, so to speak. And today we'll focus on a special version of random forests. Now, what is a random forest? Well, this question is actually a little hard to answer on a superficial level. But once you start to think about random forest as a statistical model, it might come to your mind that in a regression context, every regression model is a model for condition distribution. This is what we are all about. So random forest is a regression model, so a random forest is a model for a conditional distribution. So we have the probability that our response is smaller than something, conditional on the state X of the explanatory variables. And this is what we want to estimate. Okay, now I'm going back to statistics 101. Parametric statistics, maximum likelihood estimation. What we are doing there is, before we start looking at data, we write down a family of distributions. And this family of distributions is indexed by a parameter theta. So once we have the theta, we know what the distribution is. And we believe, or actually all regression models assume this, that the conditional model belongs to this family. And the reason why we do this is because the task of estimating a distribution function is then simplified to the task of estimating the parameter function. So the only thing that you need to know is what is the corresponding parameter for my new observation. Now, then, of course, we need some data to do something reasonable. So we're observing something, so we have the learning data, and each datum gives us a function of the parameters that's called the likelihood contribution. So Li of theta of xi gives us the unconditional, evaluated for this unconditional distribution, likelihood for some observation with some candidate parameters. And the nice thing about likelihood theory is that you can handle arbitrary measurement scales, also like problems like censoring and truncation in the likelihood function. So it's not in the model, it's in the likelihood function. So this is clearly separated. And the suggestion I want to discuss today is to understand a random forest as an adaptive local likelihood estimator. And the core idea is that you are maximizing the likelihood only in an environment that's specified by the x variables. Okay, so the conditioning here only works via these weight functions. Now, you're probably confused. I also was confused in the beginning, so let's begin, reiterate. Statistics 101, this is the unconditional maximum likelihood estimator, as we all know and love it. Okay, now we are moving to trees. So what is a tree? A tree is just a partition of the covariate space. And we are fitting these models separately for each of the cells, so of the terminal nodes of this tree. So the weights are just 0 and 1. Am I in this terminal node, weight is 0 or not? Then weight is 1. That's also simple. Now, what about forests? The core idea is also relatively simple. So we have a collection of trees, They are fitted somehow, so I'm not going into details there. But you have multiple partitions of the covariate space. And when you have a new observation, you're sending this new observation down all the trees. And for each observation in the learning sample, you record how many times they ended up in the same terminal node. And this gives us a measure of similarity, usually called proximity in this context. And then we are using these weights W that we get. They are essentially 0 for observations we don't want to take into account because they are too far away, and very high for observations that are very likely to be extremely close to our new observation in this adaptive local likelihood estimator. And then we get a parameter, a set of parameters that describe or give us the distribution, condition distribution, given this specific X we are interested in. Okay, that's nice. We are done, are we? So we just use the random forest package and pick one distribution we just like, and then we use these so-called near neighbor weights, and then we are done. Actually, this is not that new because multiple packages already rely on this reasoning. So the party and party kit packages from the beginning use these nearest neighbors weights, and also quantile regression forests fitting the quantile, conditional quantile function rely on these weights. But there's a problem. And this is the illustration of this problem. It's a very simple situation. I have 10,000 observations, so this is not a small sample problem, just one X. And there is a break in the variance. Okay, so the mean stays the same, and it's just a break in the variance. And then we have two procedures. So QRF is the quantile regression forest. And when you look at the 80% prediction intervals, you see that the quantile regression forest has a hard time picking up this break. And when we look at the corresponding prediction intervals for the transformation forest, you see that the transformation forest is basically overlaying the true red prediction intervals. So why is this? The problem is that the classical trees were designed to pick up changes in the mean. So whenever the mean changes, you implement a split, okay? But what we need is changes that are sensitive to distributional changes, and that means changes in higher moments. So when you use RPART or random forest, you just can't detect a change in the mean by design. And well, the suggestion is to use a tree method, Taylor tree method, that's able to pick up these signals. So we have to use, or I suggest, or I'm using a transformation model as a unconditional transformation model as a candidate model for this family of distributions I started out with. And this is too hard to explain here, so if you're interested in the details, it's just a very flexible parametric family, okay? And if you're interested in the details, just Google MLT for most likely transformations last year useR, and then watch it on Microsoft Tele. And the nice thing is that the normal distribution is included in this family, so when we use this parameter d equal 1, then we get a normal distribution where the mean depends on the x. That's nice, that's something we want to have, but also the variance. And this is actually new. And in 20 minutes, Lisa will make your life a little bit easier by referring to the classical distributions in this setup, okay? Now, a transformation tree heavily borrows from the idea of model-based recursive partitioning introduced 10 years ago. So we start with a maximum likelihood estimator, so no partition at all. We throw in all the data. And then we search for parameter instabilities that can be explained by the explanatory variables. That's the core idea. And this allows us, because this family is so flexible and has parameters basically reflecting distributional changes, that we can find changes in the mean and in higher moments. And then once you have the tree, it's easy to go to the forest because you just have to use the nearest neighbor weights. Now, on a more philosophical level, implementing this algorithm has also nice consequences, because we can now understand the forest as a parametric model. For each single observation, we have a simple unconditional parametric model we can understand. And that means we have the parameters, we have the likelihood, we have prediction intervals, we have the quantile function, the density function, the hazard function, cumulative hazard function, the whatever function describing the distribution. We have likelihood-based variable importances for truncated and sensor data and everything. We can sample from the forest, so you can use the forest as a model, you can draw samples from it, and the whole thing is applicable without any pain to censored and truncated data. Now, this probably didn't convince you, so I picked an example. So this is an example where we are actually interested in looking at the body mass index distribution in Switzerland. So we have a population survey, 1,650 persons participated in this survey, and we have the body mass index, and which we learned today is a Belgian concept. And we have sex of the person, age, and then lifestyle variables like smoking, status, education, physical activity, and so on. So when you just take sex and smoking into account, and then you fit these transformation models and represent them using the density, you see what you wanted to see, namely that the BMI distribution in women is stochastically smaller than the BMI distribution in men. This is expected. And you see non-normality, of course, so just going for a normal distribution is probably not going to fly. And there might be some effects of smoking, especially for the heavy smokers. And now we are using the technology I just described to bring in the other lifestyle variables. So this is a transformation tree. And the tree has two parts. One is the structural part explaining how the partitioning actually was implemented, and the prediction part, if you want, is a visualization of the corresponding densities in all the cells. And what you see is the most important take-home message from this picture is the distributions change not only with respect to the mean, but basically with respect to all higher moments. Okay, so when you look at the variables, so the tree tells us, okay, the main difference is between males and females. This is kind of expected, and then there are several splits in age and some splits in education. And the most pronounced difference is on the bottom between female teenagers and on the top older, well-trained or heavy educated men, and the difference is kind of what we expect. Now, going for the forest is a little bit harder because, I mean, fitting the forest is easy, but looking at the forest is harder. So what we first did was we looked at the variable's importance, and the variable importance tells us the same story as the tree. It says male versus female is the most important distinction. And then we have age and also education, and the other variables are less important. Now, how can we visualize this tree? So I restricted the number of parameters, so I'm only looking at age, sex, and smoking status, and then I use the idea of partial dependency. So I'm basically integrating out all the other variables, but what I'm visualizing is now the conditional distribution function. So each line represents a quantile. So we have the median, and then we also have the 90% and 10% quantile. So what we can do now is something that we can't do with the classical random forest technology. We can discuss how these variables impact not only the mean, but also the higher moments. So for example, in the top row, we have males, and then we see in the males that there is, so the youngest participants are 18 years old, so when you're 18 and then you start, well, the size doesn't change anymore, so you start putting on weight. And then there's a bump in the late 20s, and this is clearly due to too much beer and not exercising enough. And then we go to the females, and then we see that it's pretty flat in the late teens and early 20s. And then in the late 20s, there's a bump. And this bump is not due to Swiss chocolate. This bump is due to pregnancy and breastfeeding times, because you give birth to the first child usually around this age. And then you see all kinds of interesting things going on. For example, the variance increases with age. This is also something that would be expected. And this is something you just can't pick up when you're just looking at the mean. So you get the whole picture in terms of the conditional distribution function. Okay, so let me sum up. In a way, the idea of looking at trees and forests as adaptive local likelihood estimators for a conditional distribution helps us to marry the parametric statistics 101 paradigm with non-parametrics. So we have parametric families for the conditional distributions, but the way the the parameters are regressed on the explanatory variables is highly non-parametric. So this parameter function can include smooth functions and interactions and everything. So it's very hard to look at these models, especially the random forest, but I advocate the use as supermodels because they're basically making no assumptions. So when you have a simple model that is as good as the forest, you're good. You can compute predictions, predict distributions, not just means. You can have the parametric bootstrap. You have variable importances of all kinds based on the likelihood due to this fact that you inherit this simplicity, and it's applicable to censored and truncated responses. If you want to learn more, there are 2 technical reports out, one on the technology and one on this application I just presented. And then I hesitate to say that there's an R package. Because, I mean, there is R code, but there's basically no user interface to it. And Toby is actually the first adapter. And he really, he can tell you, he had a hard time getting this up and running. So if you think you want to use this technology, or you have to use this technology for a specific problem, write an email to me, and I'm happy to help. Thank you very much.